Here's a Tucson street scene captured with the Samsung Galaxy S23 Ultra. We're looking at the image in Photoshop. It's captured in JPEG. We can zoom in and look at the image in more detail. So keep looking in, and maybe we'll look at the spikes on the cactus, and we can go over and look at the face of the cat. Keep coming in. Saturation, the color on the image is spectacular. I'm not sure that it's realistic to the actual colors of the object, but if we keep zooming in, we see pixels. And so obviously the real image didn't have these pixels. But it's not bad. It's very smooth, very pretty. The Samsung also allows us to capture in RAW mode. The Samsung actually has a 100 megapixel sensor, so I'm not quite sure how they process RAW mode, and it gives you the color images in RAW mode. But anyway, it's given us a DNG image that here we've brought into Photoshop. If we keep zooming into this image, the colors are not quite as well processed, and you see a lot more noise on the object. That this kind of structure on the object is not real. Presumably it's a blue object, but we also see this pixelization. Our episode today, we're going to talk about how we should display images, and obviously if we keep zooming in and see pixels, we're not really displaying our best estimate of the underlying image. Here we can compare this raw format image with the JPEG, and we see a lot more of this kind of splotching in the raw image. The JPEG is a lot smoother because Samsung presumably has done some denoising and averaging to get rid of that. But they've also then gotten rid of some of the structure. Here on the neck, you see there's really no structure here underneath the chin of the cat. But if we go back to the raw image, there's detail there that's real detail on the image that the processing into JPEG has lost. We don't really want to see these pixels; those are not real. So what we can do is upsample the image, and here's the raw image upsampled and then saturated a little bit to make the color more similar to what Samsung gets with the JPEG. And here, now we don't see these pixelization around the eyes anymore, and the detail on the neck has been enhanced by this upsampling. This was upsampled with Photoshop itself. We know from the Shannon sampling theorem that we can upsample using the Shannon interpolation. An approximation of that is Lanczos interpolation, which uses a truncated version of the sync to do interpolation. So here's a 4x upsampled version of the image with the Lanczos interpolator in OpenCV. You see that we don't have any pixelization around the eyes. We've still got detail around the neck. In general, as we'll talk about in today's episode, we should upsample images if we're going to zoom in, and we shouldn't treat images as something like this, where we're just going to look at it as a beautiful image at whatever format it came in. We should look at it something where we should expect to zoom in and see details. Now here, there's a lot of noise. We could try, instead of this Lanczos interpolator, we could try neural interpolators that will estimate the image with upsampling. This is a multi-scale deep resolution network, which was kind of state-of-the-art 8 years ago. I think you could do much better with kind of state-of-the-art neural super resolution, but this gives you a general idea. Now here it's kind of amplifying some of the noise because it's interpreting it as some of image, but it's keeping the detail on the neck. And of course this is 4x upsample, so as we zoom in we have to go quite a ways in before we see any pixelization. We can use a variety of different neural algorithms. So this is the multi-scale deep super resolution. This is enhanced residual deep super resolution by the same group at Seoul National University. And you see again that we can zoom way into the image and not see pixelization, and presumably get better representation. And things that are lines, like here this black should presumably be a line, and it's not really interpreted that way by this neural estimator, but some improvements have been made to the image. This is the question we have in computational imaging that we'll talk about in the next two episodes. Number one, as we have image data that's pixelated from our sensors, we talked about in the last episode, how should we display that image? In general, we should upsample it, which will create more pixels. But at the same time, the purpose of a camera is to take this very high pixel count optical data stream and turn it into compressed data that we can meaningfully process. And so we're also going to be interested in compression of the image data. And those two topics, upsampling for display and downsampling to compress data, are the topics of our next two episodes. Computational imaging. Episode 56, Interpolation. Here we're looking at discrete samples. So this shows curves, but the data is actually sets of points. And we're sampling the function just sine of 2 pi x, but we've shifted the phase from one version to another. This is sampled at better than Nyquist. This is about 4 samples per wavelength. And so according to the sampling theorem, we should recover the signal exactly, but we don't recover the signal, and the samples look different even though they're all basically the same function. So what we need to do is apply interpolation to recover the original signal. If we use linear interpolation, that means we take a line between nearest neighbors and add data. But as you see here, that doesn't change the data at all. We've increased our sampling from around 50 samples to around 500 samples over this interval, but the data still looks the same. We need to use an interpolation function. So the sampling theorem suggests that we should use the sinc interpolator. So we have these discrete samples, and we interpolate with the sinc function. And in this case, we're not quite using the sinc function because the sinc has unbounded tails, and so interpolation with the sinc is computationally intensive, although we'll use an approximation to it in just a minute. Here we're using the cubic spline. The cubic spline is autoconvolution of the zeroth order spline is the rect function. The first order spline is the autoconvolution of the rect, and we keep convolving this rect, and we get better and better approximations to the sinc as we go to higher order splines. But here the cubic spline does a very good job of interpolation to recover obviously the same signal for all these different sampling phases. So this same kind of interpolation with an interpolation function can be applied to images. We have a notebook as part of our GitHub site that implements various kinds of interpolation. And here we're comparing raw data on the left for an image with details shown below, and upsampling with the Lanczos. Lanczos is a sinc interpolator, but with the truncated tails of the sinc. And you see that we get a much smoother upsampled image with 4x upsampling. So we've gone from 512 by 512 image to a 2000 by 2000 image on the right, and rather than seeing pixels as we zoom in, we see the interpolated data. Now, this is a necessary thing, that as we've got samples from data, our best estimate of the scene is not the raw pixel data. We always expect that if we want to show the signal that underlies the signals as accurately as possible, or with our best estimate of the signal, that will involve interpolation. We can use linear methods, as shown here, or we can use nonlinear methods, like neural interpolation. So the example in the introduction used this enhanced deep residual networks for single image super resolution. Personally, I wouldn't call this super resolution because that implies that we're getting better than expected resolution, but as we've seen, interpolation or upsampling is a necessary part of image estimation from data, and it's not surprising that our best estimate of an image involves more samples than were used to measure the image. But this is obviously a very hot and interesting topic. You see this paper has 8,000 citations, so many people are interested in this method for best displaying images. This particular paper won this challenge in 2017 that we'll talk about in just a second, and it did it with these residual blocks. So it does recursive processing with a feed-forward block to keep the estimation consistent with the underlying image. Results from this study, look like this. So here you see something. Well, first of all, we're looking at bicubic interpolation. We could use better linear interpolation possibly. And you see that in this particular example, the SSIM is spectacularly good, but we're looking at kind of a periodic structure that gets some aliasing from the underlying sampling, and the neural estimator is able to remove that aliasing and recover these straight lines, as you see, and we're comparing it here with various earlier neural interpolators. It does well compared to Lanczos. So here we're looking at an image from the GitHub site where we have Lanczos on the right and EDSR on the left, and you see EDSR does some denoising and smoothing that makes the image look more consistent than the simple linear method. The underlying point of a neural method is that it should recognize patterns like edges or underlying features in the image that can be used to make a higher level interpreter. So we don't have to interpret based simply on linear local interpolation. We can recognize features in the image and improve our estimation. There's a notebook that this Eugene Xiao has put online to compare a whole bunch of different neural interpreters. Our GitHub site has implemented that on some of the examples that were shown. For example, the cat image at the beginning is on this GitHub pattern. You can go look at a bunch of images, but these are all prior to 2020. This is a rapidly developing area, as you see from the 8,000 citations to the EDSR paper. Many people are working on this. There's an annual challenge, this new trends in image restoration and enhancement is part of CVPR, and there's an annual challenge to see how well you can do. People take image data sets and downsample them by a factor of 4 and then attempt to recover the original 4x upsampled image. And then you can compare different algorithms, of course, for this challenge because you know the ground truth of the upsampled image. And in this case, people are not doing as well as the example image that was selected in the EDSR paper, but they get somewhere here close to 32 dB in the PSNR. And you see that this has gotten so intense that people will get excited about 0.5 improvement in PSNR is regarded as outstanding and advanced. The main trend relative to the EDSR paper, which used residual networks, is of course to use transformers. ChatGPT is a transformer network, part of large language models. Transformers recognize context in language. They analyze the language from its context, and the same thing can be done with images. And if you recognize attention and features in context, you will get better estimators. The Xiaomi MM uses a Mamba network, which is a more efficient way to recognize context using what's called selective state space models. For us, the details of neural processing are not important in the context of this course. The main point that we're making is that it's a necessary part of the image formation process. First of all, in the last episode, we talked about what it means to extract discrete samples from images. Once we have those discrete samples, interpolation is a necessary part of forming the image. That wasn't done, of course, with film, but in the age of computational imaging, interpolation is an essential piece of image formation. Now, usually, though, interpolation is not the main problem, and you may wonder why is it that interpolation is only recently becoming popular with images? Why hasn't this always been done in digital imaging systems? And the reason is that it's expensive. Here we're going to talk about next time, which is image compression. That it's just very expensive to maintain the full data load of a camera. Going back to our cactus image that we talked about in the introduction, let's look at the files that were involved there. The DNG file, the raw data file, was 33 megabytes. The compressed JPEG file is 3.5 megabytes. This is a 12 megapixel image, so the JPEG image has about 1/4 of a byte per pixel, whereas the DNG file somehow has close to just under 3 bytes per pixel. When we upsampled it by 2x, so it's a 4x increase to a 48 megapixel image, suddenly the file size in Photoshop bloomed up to 200 megabytes or 230 megabytes. So this is actually the main issue with cameras. A camera takes image data coming in from the optical field, and we simply don't have the capacity to process and transmit an independent value for every pixel. So the basic function of a camera is to make the image data more compressed so that we can process it. And that's what we'll talk about in the next episode.